Let's look at mirror images or reflections of the sine graph. If I look at the green graph, which is again the mother graph of the regular sine function, just the ordinary y equal to sine theta in relationship to y equal to sine minus theta. In other words, what we did is we changed the sign of the independent variable. So let us see how it affects the graph. If I now look, for instance, at the value of minus 90, so if I look here at minus 90, what will happen if I take minus 90 and I multiply it by a minus, then I get plus 90. So what I do, I read off this value and then I will plug it in k. In other words, I take the minus 90, multiply by minus, read off on the original graph and make a dot there. If I take, for instance, minus 180, I will go to plus 180, read off the value and make a dot there. If I go to minus 270, I will multiply it by a minus to get 270. I will read off the value here, which is -1, and then I will take that value back and make a dot here for -1. So in this case, doesn't matter whether I start at the negative side or the positive side. What I see is actually what happens on the left-hand side repeats on the right-hand side and vice versa. So in this case, I have a reflection about the y-axis, or it is mirrored in the y-axis. Mirror images or reflections is another word for mirroring. So if I look again at this function at the period, I see it's just the same as the regular function, 360 degrees. The amplitude is the same. The roots are exactly the same because it's still at A and C and E and G, etc. And the general formula for this, if I take sine theta and I solve that, sine of minus theta equal to 0, then if I first solve sine theta equal to 0, I get theta equal to k times 180 degrees. And you can check here 0, 180, 360. But if I now solve that, I get minus theta equal to k times 180 degrees, k element of z, which is just the same as theta equal to k times 180 degrees, k element of z, where this k is just now the negative of that k, but we will still get exactly the same values for all the points. In this case, we will still have the extremes exactly the same, y equal to -1 and y equal to +1, but in this case, our minima, the y equal to -1, where it previously appeared at minus 90 degrees, it will now appear at plus 90 degrees. So that will now become plus 90 degrees because I multiply with a minus. So we can see here the minima is now at J and L, where it previously was at D and H. D was minus 90, now it's at plus 90. It was at 270, now it's at minus 270. Similarly, the maxima will be, previously it was at 90 degrees, and now it will happen at minus 90 degrees. So, and other maxima was at B at minus 270 degrees, but now the new maxima will be at plus 270 degrees. So that is the mirror images or reflections about the y-axis. In the next case, what we do is, now the minus is in front of the sine theta, so we actually multiply sine theta with -1. So what happens if I take, for instance, the function value f, which is +1, it will give me a value of -1. And if I take a value of -1 here, it will give me a function value of +1 there. If I take this -1 and I swap it, it becomes +1, and if I take that one, it becomes -1. So in this case, it's a reflection about the x-axis, or it's mirrored in the x-axis. So the identity in this case, if you look at the two graphs on the different pages, you will notice we have exactly the same graph. The red graph and the blue graph are exactly the same, but we did different paths, and that gives us this identity, that when we have sine of minus theta, we get equal to minus sine theta. So that's our identity that we have. When we also have the cast rule, then we do it in the same way. Again, we look at the period. Nothing changed to the period. It's still the same. The amplitude is still the same. Even the roots are the same, because now if I look at minus sine theta equal to 0, it's exactly the same as when I solve sine theta equal to 0. So I again get theta equal to k times 180 degrees. K is an element of z. And you can notice it's exactly the same places A, C, E, and G, and I as before. If I look at the extremes, again it's y equal to -1 and y equal to +1. Again, the minima swapped with the maximas, and the maxima swapped with the minima, etc. So you can write down that formula also. To summarize, the reflections, I've included again the first graph, the one of sine minus theta, the red graph, versus the blue graph, which is minus sine theta. And we see that the red graph is a reflection about the y-axis, because what happens here happens there now. What happens at M happened at B before, etc. And in the case of this function, we have a reflection about the x-axis. In the end, we see these two graphs is exactly the same, so we have the identity that sine of min theta is equal to minus sine theta. So please take a look at this, and when you now want to do a bigger amplitude, like for instance -2 sine theta, then you will not say it is stretched with a factor of -2. It's still stretched with a factor of +2, but it's also reflected in this case in the x-axis.